Section 23.3 deals with motional EMF. Now remember flux, we define flux as B times A times cosine of theta, where again theta is the angle between B and A. In this case, B is into the page and A is also perpendicular to the page. Now the situation we have is a resistor, a couple of rails on which this thick bar slides. So we have a circuit, there's a closed circuit here where there's a loop of wire, and because we have a loop of wire, there's a flux here. This rectangle has dimensions L by X. And actually, I'm going to draw the earlier position of the bar. The bar is moving to the right at speed v, and so it was at an earlier point in time at this position. So I'm going to call this X. And as the bar slides to the right, the area is getting bigger. So in some time delta t, the bar has moved a distance delta x to the right, and the velocity relates those two quantities. Delta x over delta t is how fast the bar is moving. We have a flux. There's a magnetic field flowing through an area of a loop of wire. So there's a B, there's an A. The angle between them is 0, so cosine of theta is 1. And the area is changing. In this case, the magnetic field is staying constant. It's uniform, but the area is changing. And so there will be a change in flux because the area is changing. So what is the EMF produced by that changing flux? In this problem, there's just one loop of wire. We're looking at the change in flux, BA, cosine theta. But again, theta is 0, so cosine of 0 is 1 over change in time. And so then the EMF is simply the change in the area. But the dimension L is not changing, and so the EMF then is BLV. It's important to note in this particular problem that B and L and V are all perpendicular to each other, and that is an important thing to know when you're using this equation, is that the EMF produced is equal to BLV when these three are perpendicular to each other. If they were not, then there would be other angles involved here. We're going to come back to this idea later on when we look at generators.